Just more electrical physics here. We're going to look at a nice little problem involving the photoelectric effect. All right, so we're going to take ourselves a nice photoelectric effect system, and I've already done this, but here we got ourselves a collector, we've got ourselves an emitter. We'll go ahead and throw in some potential difference here. Doesn't really matter at this point. Let's go do it like this. And there is some potential difference. We're going to go ahead and shine some light over yonder. And greenish would probably be a little bit more suitable here. But we're going to shine some light. And we're going to say that this light liberates some photoelectrons. And we're able to make it over here, substantiate some current, whatever. Really, we're not going to worry about the current right now. But anyways, this is what we've got going on. All right, so here's the problem. All right, so we're going to take light that has a wavelength of 564 nanometers. And it is equal to 564 nanometers. We're going to shine it on this, and we're going to say that the electrons that are emitted have a maximum speed right when they're ejected of 30,000 meters per second. So V max, and we'll say initial, is equal to 30,000 meters per second. And then we're asked some various things about this, like, hey, what's the work function of this material then? What's the cutoff wavelength? What's the cutoff frequency? What's the stopping potential if we change the wavelength of light to something else? So that's what we're going to get to. So we go by this one by one. The first question is, A, what's the work function of this material then? Well, the work function of the material can be summed up by KE max is equal to E sub gamma minus V. That's it. So we can define the work function then, phi, as being equal to E sub gamma minus the maximum kinetic energy, and that's when they're actually liberated. So there we go. We've got this going on. Well, let's just go ahead and do this. Phi is then equal to, well, since we've got the wavelength there, let's write this in terms of hc over lambda for the photon energy, and that minus the maximum kinetic energy of the liberated photoelectron. So this is what we need. The kinetic energy is 1/2 the mass of an electron multiplied by its max speed squared. So there we go. We've got all this good stuff. We just need to go ahead and compute this out, right? So some things to remember. H is equal to 6.626 times 10 to the negative 34 joule seconds. C, we'll just say, is 3.00 times 10 to the 8th meters per second. And we've got the wavelength. We need m sub e as well. M sub e, the mass of the electron, we'll just call it 9.109. Let's say 9.11 times 10 to the negative 31 kilograms. These are all SI units, so let's remember that. All right, so let's just go ahead and calculate this out and say, all right, from this, we've got ourselves hc over lambda. I'll leave h and c like that. hc divided by lambda, don't forget that's in nanometers, so we'll go 564 times 10 to the 9th meters minus 1/2 m sub e times v squared, which is 30,000 meters per second quantity squared. We'll compute this out and see what we get. All right. Equals 3.52036 times 10 to the, well, this should be 7 there, 0.037 times 10 to the negative 19 joules. Well, there's the work function, but that's in joules, right? Well, generally we don't want the work function in joules, we want it in electron volts. So we've got that 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. That again is the energy that 1 electron gains when accelerated to a potential difference of 1 volt. That's how much. And thus we'll get that phi in electron volts is going to be this divided by this. So just a little nice conversion there. And that. 2.197, sure, 2.197 electron volts. There's the work function of this material. Yay, we defined it. Fantastic, fantastic. All right, so what else could we do with this? Well, we can go ahead and say stuff like, well, if that's the work function, what's the cutoff wavelength? And what's the cutoff frequency? So if we ask for the frequency first, we want F sub C equals what? So again, if we go below a certain frequency, we will no longer liberate photoelectrons because the photons won't have enough energy to do so. So that's what this is, the cutoff. So basically the minimum frequency that will just liberate an electron. Below that, nothing. So from this, again, we've got 0 is for the kinetic energy is equal to H F sub C minus phi, giving us that F sub C is equal to phi divided by H. All right, so again, this is where things come into play. You've got to be a little bit careful. We don't want to mix up electron volts and SI units here. So we've already got the work function there expressed in terms of joules. So utilizing it in terms of joules and then joule seconds for H is the smart way to go. Otherwise, you can convert H into electron volt seconds. That would be okay too, but ultimately, both should be same unit system. So we can write them out in joules and joule seconds. 3.52037 times 10 to the negative 19 joules divided by 6.626 times 10 to the negative 34 joules seconds, which will give us 1/seconds, which is hertz. And let's come here to that, divide by 6.626 to the negative 34. We get ourselves a frequency of approximately 5.330, we'll just call it. 5.330 times 10 to the 14th hertz. You say, wow, that's a lot of hertz. Well, yeah, that's light with a small wavelength. What wavelength is that? That's usually a little bit easier to get an idea of. So we come over here and we say, well, part C is asking what is the cutoff wavelength? And we could go back through and calculate it out through HC over lambda minus phi is equal to 0. Or since we've already got the cutoff frequency, we can just use standard wave relations to figure out what the subsequent cutoff wavelength would be. Because V, actually, let's not say V, C is equal to lambda F. So that has to hold for light. C is the speed of light, lambda is the wavelength, F's the frequency, and thus we get that lambda sub C is going to be equal to C over F sub C, which is then 3 times 10 to the 8th meters per second divided by 5.330 times 10 to the 14th hertz, which gives us 5.646 5.646 times 10 to the negative 7. 564.6 nanometers. So there's the cutoff wavelength. And we were using light with a wavelength of exactly 564 nanometers. We're really close to the cutoff wavelength / cutoff frequency there. We increased the wavelength by just 0.6 nanometers. Boom, we're at the cutoff wavelength, and below that we get no more photoelectric effect. But that's just how this is all working out here. All right, so one last question here, and that is, if we change the light to having a wavelength of 410 nanometers, what stopping potential is utilized or should be utilized in order to prevent any substantiated current? What's the stopping potential? V sub s for this system with this particular material and this wavelength of light. What potential difference do we need in order to stop the current? All right, so what did we have with all of this? Well, we had that the stopping potential E V sub s had to be equal to the initial kinetic energy here. And yeah, basically, if that was the case, then that's what we've got going on. Well, the initial kinetic energy is dependent on the work function and the wavelength of light being used. So we've got ourselves that E V sub s is then equal to E sub gamma minus phi. And then we can expand this out. E V sub s is then equal to hc over lambda minus phi. And finally, from this, we could solve this out for V sub s by dividing both sides by E, the absolute value of the charge of an electron, and get ourselves that V sub s is then equal to hc over lambda E minus phi over E. Looks good. All right, so we'll go ahead and take this on over here. We got hc, we've got lambda, we know what E is, so we can write this as the hc divided by lambda, in this case now is 410 nanometers. 410 times 10 to the negative 9 meters. That should have been the negative here. And then we've got times 1.602 times 10 to the negative 19 coulombs. And we've got that's minus the work function of the material, which again, be careful if this is electron volts here. It'd be best to just go ahead and use joules because everything else over here is in joules. So we can write this as 3.52037 times 10 to the negative 19 joules divided by, well, charge of an electron, 1.602 times 10 to the negative 19 coulombs. Oh, look at this. This number here, I'm not going to have units of electron volts, but it's going to be the same thing that we got here, same numeric value. Anyways, doesn't matter. We still calculate this all out, and we get ourselves V sub s is going to be equal to hope I'm not messing up putting stuff in here. We've got 2.5237. one moment here. Put something in here. Badly. Six. Oh, jeez. 1 second. Got a little calculator issue going on. Came out with some crazy number and pushing the wrong buttons here. So I just want to insert E to the 19. There we go. 0.8289. 0.829, we'll call it. So even though we've reduced down the wavelength quite a bit to feed more energy into the liberated electrons, we still don't need that high of a potential difference to stop the electrons from making it from the emitter to the collector in this particular case. All right, well, that's pretty much that. And fun little systems, cool though. We'll leave it at that. Be well, have a good one. Until next.